Well, howdy there, Internet people. It's Professor Leach again. Today, we're going to talk about addition, multiplication, and exponents and expand that to include polynomials. But before we do that, we want to introduce the idea of function notation. When we're talking about function notation, all we're really doing is giving names to expressions that we're going to be working with. That's how we can think of function notation. We are going to give names for expressions. So functions are just going to be names for expressions. So for example, suppose we're going to be working with the expression, suppose we have an expression like 3x squared plus 5. So the expression is just a list of things that we're going to be doing to x. We can evaluate the expression for a value of x. So we can do what's called evaluate the expression for some number x. So x equals 7. So what that means is that we replace the x with the 7. We're saying x equals 7. So now we're going to make the x equal to a 7. And it's the expression itself is just a set of instructions for what to do to the x. So this, we're thinking of this as a set of instructions to do to x. It's a list of things to do to x and a particular order in which to do them. So when we evaluate the expression, we replace the x with a 7 and then simplify. So our expression is 3 times a thing squared plus 5. So if I put the 7 in for the x, we just simplify this following our rules for how we simplify things. We know that exponents go before multiplication, and multiplication goes before addition. So I'm not adding 5 yet. I have to do 7 squared first. I'll multiply the result by 3, and then I'll add the result, add 5 to the result. So following, we know that exponents go before multiplication. 7 squared is 49. And then we're going to multiply this by 3. Multiplication goes before addition. So 3 49s is 120 and 147. And then we add the 5. 147 plus 5 is 152. So here, when we evaluate the expression for x equals 7, we end up with 152. 152 is tied to this value of 7 through this expression. One of the things to note here is that when I calculated 3 times 49, I used a little bit of the stuff we were talking about yesterday. So 3 49s, we could think of this as 3 times 40 and 9. So I read 3 times 49 as 120 and 27, or 147. You might have used a different strategy. You might have said, no, I don't want to have that plus 9. I want to think of the 49 as 50 negative 1. So 3 times 50 is 150 minus 3. That's also 147. So we're just trying to use different strategies for how we cope with these numbers. We could also said 49 is 3 times 100 minus 51, and then it'd be 300 minus 151, which is still 153, which is still 147. That would be a strange way to write 49. The most common ways we'll think of 49 as 40 and 9 or 50 and -1. Good ways to get to 147. So it could be that we want to use this expression a lot, so much so that we want to give it a name. And we're going to call that, we're going to use function notation. There's more that goes into a function than just the notation, but the notation is the first thing that we encounter. So it could be that we want to keep track of a bunch of different values for this expression. And so the 7 and the 52 are connected in this expression. Sorry, the 7 and the 152 are connected through this expression. So note, this expression connects the 7 and the 152. So it's not just the 152 that we want. Might want to remember that this came from 7. This is what happens when we evaluate this expression for 7. Function notation would be a way of putting those two together. So we could name the expression. Let's give our expression a name. Functions don't normally get interesting names. They get one-letter names, and the first one that we use is f. So we define f of x. We write f is the name of the function, and in parentheses we put an x, the variable that the function employs. And then we write equals the expression that we're using. So this symbol here is pronounced f of x. F of x is pronounced f of x. F is just the name of the function. The name of the function is f. The of x part says the variable that the function uses. X is the variable the function employs. And then we just say have an expression. That's what the function is asking us to do. 3x plus 5 is what we do to the x. So we could think of it, the way I usually think of it is the expression is what f does to the x. So to evaluate this function, 3x squared minus 5, you take the x and square it, then you multiply by 3, and then you add 5. If I wanted to say evaluate this function for 10, I would say, if I want to plug x equals 10 in, I could say find f of 10. The expression says take 3, multiply by the x squared, and then add 5. So we just replace the x with whatever's in the parentheses, and then we simplify the expression. 10 squared is 100. 3 times 100 is 300, plus 5 is 305. So that's when I give you a function, say f of x is 3x plus 5, I'm just naming a function. I named the function f here. And when I say find f of 7, that means evaluate this expression when x equals 7. When I say f of 10, it says evaluate the expression for x equals 10. So that's what this set of instructions is. So this says evaluate the expression for x equals 10. So it was really just this problem on the quiz, or this question on the quiz, was really just like all the previous questions on the quiz. Evaluate the expression for a given value of x. I just asked it in this kind of strange way, using this newfangled function notation. The reason that we would want to use function notation instead of just saying y equals mx plus b or y equals 3x squared plus 5 is that when we, instead of just saying 305, we're saying f of 10 is 305, and we're making a relationship between the 10 and the 305. We're saying an input of 10 will give us an output of 305 through this function. So it connects them all. Input of 10, output of 305 through the function named f. Any questions? So I'm just introducing our fancy function notation. It's often very handy to just give names to expressions. So that, and we do this all the time. Instead of saying something like the opposite of b plus or minus the square root of b squared minus 4 is c all over 2a every single time, we just say the quadratic formula. We give it a name. But since the expressions are going to change a lot in a math class, we just say, okay, just one letter names will do. That'll be fine. So we call them like F and G and H. And we just start with F because that stands for function. But it's important to pronounce f of x correctly. It's f of x. And it does not mean that we're multiplying f times x. Just whatever's in the parentheses, that's what gets replaced in the function. It's one of those times where the parentheses we're not just juxtaposing two variables. Normally, if I say, here's x times y, or xy, that normally means take x and multiply it by y. But in this case, f is not a variable. It's the name of a function. It's a whole list of things to do. And we want to apply it to whatever's in the parentheses. Any questions? Comments? Reports? So this actually works great. We define this expression 3x squared plus 5, and I did this on the quiz as well. I started giving you polynomials to evaluate. 3x squared plus 5 is a polynomial. A polynomial is just a sum of a bunch of multiples of powers of x. That's way too fancy a description for what we want to do with these things, but that's our description nonetheless. A polynomial let's look at polynomials. Oops, oh, this is 120, right? And it's still 3. Okay, let's look at polynomials. I'm glad I got all that recorded. Writing a page is at the top, and then I just immediately hide it. Let's look at polynomials. A polynomial is a sum of multiples of powers of x. A polynomial is a sum of multiples of powers of x. super generic description of what a polynomial is. It's a sum of multiples of powers of x. It does involve all three of our operations. So it does involve addition, multiplication, and exponents. So an example of a polynomial will be, let's see, I have to come up with one at random, 3x squared plus 5. 3x squared plus 5. It's a sum because of the plus. We're separating things into terms. The addition separates the polynomial into terms. So this polynomial has two terms in it. Of multiples of powers of x, this first term, 3x squared, is a multiple 3 times the second power of x. So this is the x squared term. It says we have 3 times the x squared. 3 times the second power of x. So the x squared term is 3 times the second power of x. It's got multiplication, 3 copies of the x squared, and we're looking at the second power of x. The other term in this polynomial is a plus 5. That's the constant term because there's no x in it. So plus 5 is the constant term because there's no x in it. Or the 0 power of x. Any questions? No, because we're all familiar with the expression 3x squared plus 5, even though we're a little bit shaky on how to read expressions right now. But we got the general shape of it. We can see the addition is separating things into what we're going to call terms. Here's an x squared term. We're going to name terms by their variables and their exponents. So it looks like terms are named by the variables and the exponents. That's an important thing to note. Looks like the terms are named by the exponents, the variables and their exponents. That's a convention that we should point out. Terms are going to be named by their variables and their exponents. Separated by pluses and minuses. Addition and subtraction is what's going to separate the polynomial into terms. In each term, we'll have a multiple, 3, there's our multiple, of a power of x. So another example, I could say have x squared minus 5x minus 6. This polynomial has 3 terms in it. Actually, I want the pluses, so just go switch these to pluses. This polynomial has 3 terms, an x squared term, an x term, and a constant term. So there's 3 terms. An x squared term, an x term, and a constant term. So there's a 3-term polynomial. We call that a trinomial. This is also what you say when your kid is a very picky eater. So you'll try no meal. That's a 3-term polynomial. If that made you groan, I want you to know that I am legally obliged to use that math joke the first time trinomial comes up. There's also the cheapskate where there's only 2 terms. That's called a binomial. That's the cheapskate who never pays. And then monomial is what you say when you come home and you're not hungry. Ma, no meal. So I'm legally obliged to drop those terrible math puns on you. So don't blame me. I mean, change the law. So we have an x term, and an x squared term, an x term, and a constant term. So we got those 3 different terms. The x, it says, looks like we have 1 copy of x squared, 5 copies of the x, and 6 just constant as the constant. Any questions? Here's how we want to look at polynomials. We want to think of polynomials just like numbers. The terms of a polynomial correspond to the digits of a number. That's the thing. The terms of a polynomial. So we want to connect polynomials and numbers. We want to connect polynomials and numbers. Here's the thinking that goes into this. Think of the terms of a polynomial as the digits of a number. Think of the terms of a polynomial as the digits of a number. So think about the terms of a polynomial as the digits of a number. But instead, where the polynomial has an x, the number will have a 10. The polynomial is like base x. And the number is going to be in base 10. So wherever we had 10s in the number, we're just going to have x's in the polynomial. So the polynomial x squared plus 5x plus 6 is a polynomial version of the number 156. So 1, 5, and 6, 1, 5, and 6. Think of the terms of the polynomial as the digits of a number. When we had the polynomial 3x squared plus 5, remember when we calculated this for x equals 10, we got 305. The x squared is like the 3 10 squareds, 0 10s, and 5 1s, or 305. So 3x squared has no x term, so that's like a 0x that we don't normally write. We don't usually write a term if the coefficient is 0. But we need that 0 in the number 305 to say that we have 0 10s. But when we're writing numbers, we need that 0. With polynomials, we're separating the terms with pluses and minuses, but with regular old numbers, we need that 0 to hold the place of the tens, to separate, to make sure that we recognize the 3 as the hundreds and the 5 as the ones. I think in some older traditions in math, they would just leave a space there, and man, that could get really confusing. Because what if you're inconsistent with the amount of space you leave between the numbers? But that was before the invention of the number 0. Great story. 0, which we think of as such an important number, is the last number that we figured out. It's the last thing that we invented. We, like I was there. It's the last number that was invented. It's like, oh, hey, what if we put just like a hole to say there's nothing there? And it's a 0. Any questions? All right. So I don't understand how, I said it before, I don't understand how Rome got so big without having just like, with their stupid number system. I mean, it's terrible. I don't know why Hollywood still feels obliged to write Roman numerals for the year of the year that you get a movie. It's ridiculous. But anyway, there we are. I want you to think about the terms of a polynomial as the digits of a number. That's how we take all the things that we know about arithmetic and apply them to algebra, by looking at polynomials and thinking about the digits of a number. Any questions? All right. So if we think about one of the things I mean is that if we look at one more example, and we've done examples like this before, but if we think of 12 times 13, I'm going to use that because I wrote 156 on the previous page. If we think about multiplying the numbers 12 times 13, we know that to multiply these, we multiply each digit of one number by every digit of the other number. We use the distributive property to multiply. So we're going to have the 10 times 10. So the 10 times 10 is 10 squared, or 100. Then we have the 10 times the 3. That's going to be 30. And then we have 10 times the 2. That's going to be 20. And then we'll have the 3 times the 2, which is 6. And when we add them all up, we get 156. The process that we use for numbers is the same process that we're going to use for polynomials. Polynomials don't always have a 10, they'll have an x instead of the 10. So if I think of multiplying x plus 2 times x plus 3, this is multiplication distributing over addition, in the same way that multiplication was distributing over addition in 12 times 13, where we take x times x, that's x squared, x times the 3, that's 3x, x times the 2 is 2x, and 2 times the 3, which is 6. These aren't fancy rules that I'm using. When I multiply a number by a variable, I just stick the 2 together. This is literally just what we mean when we say multiply. 2 times x means an x plus an x, and we write that as 2x. X times x is not x squared because fancy rules. That's literally what we mean by x squared. It means an x times an x, and that's the first thing that we do here. Then we're still under the rules that we only add things that are the same, and when we add them, it doesn't change what they are. And that's why we can take the 3x and the 2x and combine that into a 5x. But the things that we did down here are the same things that we did when we just multiplied 12 times 13. 100 is because we had 10 times 10. 30 is because we had 3 times 10. 20 is because we had 2 times 10. And the 6 is because we had 2 times 3. We use the same process in both because they're both multiplication and they both have terms. And terms are separated by addition. So we're just using the distributive property and distributing the multiplication over the addition. In both cases, we distribute multiplication. In both cases, multiplication distributes over addition. In the same vein, we have to think about exponents. Exponents mean repeated multiplication. So if I have, say, 12 squared, we know that this is 144, but let's watch it play out in multiplication. 12 squared means 12 times 12, which is going to be 10 times 10, because multiplication distributes over addition, 100. 10 times 2, 20. 2 times 10, 20. 2 times 2, 4. And we get what we already knew, 144. If we're going to, say, replace the 12 like I did up here with an x plus 2, I just write 2 copies of x plus 2 and multiply them. Just like before, multiplication distributes over addition. X times x is x squared. X times 2 is plus 2x. 2 times x is plus 2x. 2 times 2 is 4. We only add things that are the same, and when you add them, it doesn't change what they are. So I'll add the like terms, because that's sameness in polynomials. And our polynomial looks like x squared plus 4x plus 4. Any questions? This is really important right now, that we look at these two operations as the same because they are the same. 12 squared is multiplication, 12 times 12. X plus 2 squared is multiplication, x plus 2 times another x plus 2. The interaction between multiplication and addition is that multiplication distributes over addition, and we use the distributive property in both of these operations. We do not want to think about algebra as some random collection of weird rules that are just out there to torture us. If that was the case, people have been being tortured by algebra for a very long time, and so it's clearly not about you. So don't take this all personally. The rules are the way they are because that's how numbers behave. We don't write this as x squared plus 4 because that's not how numbers work. 12 squared is not 100 squared and 2 squared. It's 100 squared plus 2 copies of 10 times 2 plus the 2 squared. Same thing happens down here when we're squaring this polynomial. Not fancy rules, same rules. We're following the same operations. Any questions? Thinking about polynomials as numbers and trying to connect everything that we do with all these variable expressions that we're going to encounter with something that we already know how to do in arithmetic is critical to getting better at understanding algebra. By getting better at understanding algebra, you will get better at understanding arithmetic. The two will support each other. Any questions? Comments? Snide remarks? It's not to say that you can't do this class just by learning a bunch of separate things, but why would you want to learn 30 different things if you can learn 2 and just adapt? I'd be much more interested in someone whose skill set includes adaptability than just someone who knows a bunch of random things. Especially because if you know a bunch of random things, you're just going to start forgetting those random things unless you connect them together. It's the connections that make you remember them. All right, that's how I want you to start thinking about polynomials. And we're going to start having some polynomials are going to start to creep more into our operations, but we're still doing the same operations. So don't forget that. Anyway, it's just a thought. Y'all have a good day.